In Unit 2, Homework 7, we're looking at factoring trinomial squares and the difference of perfect squares. So to get started, let's go ahead and talk about factoring trinomial squares. Well, we know what a trinomial is. A trinomial is an algebraic expression that has three terms. So let's go ahead and look at a squared minus 14a plus 49. So our directions are here to factor. Now if you want to, you can go through the AC method process here. But what we're doing in this section is we're showing you some shortcuts to factoring. Now factoring is a huge part of algebra, and in college algebra you'll be factoring all the time. So to know some of these quick little shortcuts will really benefit you later next semester. So factoring trinomial squares and difference of perfect squares. So what we're doing is we're looking for numbers that are perfect squares. Perfect squares are numbers like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, etc. So we're looking for numbers. When I take another number like 5 and multiply it by itself, 5 times 5 is 25. 25 is called a perfect square, and the square root of 25 is 5. So if I look at my numbers here, I notice that 49 is a perfect square. Now the square root of 49 is 7. So 7 times 7 equals 49. Now look at this. 7 times 7 is 49, and 7 plus 7 is 14. So whenever you're looking at a trinomial and you're asked to factor it, there's a pretty good chance that if that perfect square pops up, you'll be able to use it to factor quickly using that reverse FOIL method. We'd put our 7s here. Now notice my 49 has to be positive. Okay, so again, my 49 is positive. So I could either have two pluses here or two minuses. One of these has to work because I have to get a positive 49. Now when I check this out though, here I get a negative 7a minus 7a is a negative 14a. Over here I'd have a positive 7 plus a positive 7a is 14a, a plus. So this method off to the right, this one does not work because I get a plus 14a. This is the one that works. I get my difference of perfect squares. When you FOIL this out, first outside, insides, and last, we should check it. First outsides and insides and lasts. I get a squared minus 7a, and again this is my check, plus 49. Combining my middle terms, I have a squared minus 14a plus 49. So this checks. So my answer is a minus 7 times a minus 7. Now, a lot of times when you rewrite these, if you notice, I'm multiplying a minus 7 by itself. So this is a minus 7 quantity squared. Also notice that it's the entire quantity that's squared, not just the a and not just the 7. So the rule is this: if you see a perfect square in a trinomial, try and use that shortcut to your advantage to find a quick way to factor that. Now again, you can still use the AC method. But if we can start to see some of these shortcuts, it will save us some time. So continue to use the AC method if these don't make sense to you. But again, once you see these perfect squares, you might want to start thinking about using that perfect square to your advantage. So our rule here is to factor. Well, if we want to factor, I notice that 25 is a perfect square. That's 5 times 5. 5 times 5 is 25. 5 plus 5 is 10. So this looks like it's going to work pretty good. So 5 times 5 is 25, so that will go in my first positions. Now w times w is w squared, so that will go in my last positions. And notice I have both positive signs here. And so when I add my 5 w's, I need them to be positive, and I need my w squared to be positive. So I get 5 plus w times 5 plus w. Now again, I can check this, and when I check this, 5 times 5 is 25. My outsides are 5w, my insides are 5w, and my lasts are w squared. I can combine these like terms. So here you can see that this checks with exactly what I started with. So my answer here is 5 plus w times 5 plus w. Now, This means I take 5 plus w and I multiply it by itself, so this is 5 plus w quantity squared. Now another way that you could see this written and would also be counted as correct is to rewrite this as w plus 5 quantity squared. So this would be an equivalent expression. W plus 5 quantity squared would be correct as well. Order doesn't matter when you add. Whether you take 2 plus 3 or 3 plus 2, you're going to get the same answer. So again, you can reverse these on how they're written and you'll get the same answer in the end. And my math lab should accept either one as well. So again, we're looking for those perfect squares. For our next one, let's go ahead and look at 9 plus v squared minus 6v. Now a couple comments about this last one. If I wanted to, I could have rewritten this as w squared plus 10w plus 25 and worked the problem from there. And this factorization would have yielded the w plus 5. So usually we like things to be in descending order, but it doesn't have to be. But we usually like the middle term to be a linear term, meaning the v is to the first power. So my directions are here to factor. And on this one I do want to rewrite it. I want to put this v squared out front, especially since it's a positive v squared, minus 6v plus 9. Okay, now as you look at this and you're looking for a perfect square, I see 3 times 3 is 9, and I see 3 plus 3 is 6. Now we'll worry about the negative in a second. So this will factor, and in my front positions for my FOIL we'll go v and v. In my back positions, 3 times 3 is 9. Now I need a positive 9, but when they add them together I need a negative 6v, so both these signs need to be negative. And so I'm left with v minus 3 quantity squared. Okay, because I'm multiplying it by itself, I can go with that quantity squared. Now again, you can check these using the FOIL method or the box method, either one, but it's a good idea to always check these. So as a quick refresher, let's go ahead and show you the box method for checking. The box method for checking would be v minus 3 and v minus 3. V times v is v squared. V times negative 3 is negative 3v. Negative 3 times v is a negative 3v. And negative 3 times negative 3 is a positive 9. Now usually on the diagonal something cool happens, as those are my like terms. And so those combine to that minus 6v. And I'm left with v squared minus 6v plus 9. So it does check. And we're happy because on a test or a quiz we know that we have the right answer and we'll get full credit for that. So let's go ahead and keep on factoring. Let's keep looking for these perfect squares. Okay, so for our next one, r to the 4th minus 16r squared plus 64. Now we're asked to factor. Now this is interesting. This is not a squared. Everything else before has been a squared. But I do see something pretty handy here. 8 times 8 is 64. And 8 plus 8 is 16. Or if you want to think about it, you need to compensate for this negative. You could also think about this as negative 8 minus 8 is equal to the negative 16. Now when we start this process, instead of having an r and an r in each of the front positions, we'll have an r squared times r squared, because r squared times r squared is r to the 4th. We'll put our 8's in our back position, and then both of our signs again have to be minus 8. So r to the 4th minus 8r squared minus 8r squared is minus 16r squared. Negative 8 times negative 8 is a positive 64. So this is r squared minus 8 quantity squared. Okay, and again, check it with the box method like we did up top, or actually write down the FOIL, but get in the habit of checking these, because there's really no reason to miss one of these on a test or a quiz, because you know before you even submit the answer whether it's correct or incorrect because of the ability to check these. Okay, so 9 plus 12b plus 4b squared. Directions are to factor. I'm going to rewrite this because the highest coefficient here is a 2. I'm going to write these in descending order. And another thing I'm looking at is the coefficient in front of the b squared is a positive number. If it was a negative number, I would leave this in the original order it was given. I see 2 square roots here. 2 times 2 is 4. 3 times 3 is 9. So when we start setting up our parentheses, and remember you can still use the AC method with this, I'm going to put 2b in my front positions, 2 and 2, and in my back positions I'll have a 3 and a 3. Now notice both signs are positive, so both signs have to be positive here as well. So my solution is 2b plus 3 quantity squared. Let's go ahead and check this one. Let's do 2b plus 3. I'm going to use the box method. Okay, 2b times 2b is 4b squared. 6b, 6b, and plus 9. Again, this diagonal, 6b plus 6b would give me that 12b. And so when I rewrite this, I have a 4b squared plus 12b plus 9, which is originally what I started with over here. So I know I have the right answer. So again, you should know before you hit submit on a quiz, or before you select whatever your multiple choice response is on the test, whether an answer is right or wrong, because you should have already FOILed it out to check it. And this will really help you with your test grade and your quiz grades as well, because of this ability to check ahead of time before you submit your answers. Okay, let's go ahead and look at 16. We're going to use the letter S here, so I'm going to try not to make it look like a 5. Minus 80s plus 100. All of these are even numbers. Up here, the 12 and the 4 had something in common, and the 9 and the 12 did, but there was not one number that was common to the 9, 12, and 4 other than a 1. But down here, I see a GCF of a 4. So I'm going to factor. So I'm going to start by pulling out our GCF. I'll be left with 4s squared minus 20s plus 25. Now here I see two perfect squares, 2 times 2 and 5 times 5. Now if you'd rather use the AC method than our shortcut method we're using, go ahead and keep up with that. Hey, but the shortcut method, if I can see those perfect squares, will really save you some time. Now I'd have 2s in each of my front positions, first, outside, insides, and lasts. Now in my last positions I'd have a 5 and a 5. Now notice the 25 has to be positive, so these either have to be both plus 5 or minus 5 minus 5. And this is the sign up here that tells me what they have to be. They have to be negative in order to get a negative 20s out of this. So if you want to double check that by FOILing it out or using the box method, you can. But because I multiply 2s minus 5 by itself, that tells me that I'm going to have quantity squared. So that's another shortcut way of writing that too. Okay, factor completely is always our directions. So let's go ahead and look at 64 minus 48v plus 9v squared. Now you really have to check these, because just because there's a perfect square involved doesn't guarantee that it's factorable. It just usually is a pretty good indicator of where to start. So on this one, I see 8 times 8 is 64, and 3 times 3 is 9. So again, pretty good idea of where I should start. It's not a guarantee, so that's why I always need to check these. So 8 would be in my front positions, 3v would be in my back positions. My 3v has to be positive, so either you just have to be both plus or both minus, but I know that they both need to be minus because of our negative sign here. So let's check our work. 8 times 8 is 64. Negative 24v minus 24v is a negative 48v. Negative 3v times negative 3v is positive 9v squared. So this would factor perfectly 8 minus 3v quantity squared. Now as a side note, you could rewrite this as 9v squared minus 48v plus 64. Now if you did that, our front positions would change to a 3v, and my back positions would change to 8s, and they would both be negative. So when I rewrote this, it would be quantity squared. So actually either of these answers are acceptable. They're both correct. And you might say, well, wait a minute, they're not equivalent. Well, remember, the only thing that differs here are the signs. So this is a positive 8 and a negative 3, positive 3 and a negative 8. So they only differ by a negative sign. And remember, when you take a negative times a negative, or a negative and square it, you get a positive back. So these are equivalent expressions. Either answer is acceptable. So whether you rewrite them or not, that's kind of up to you. Sometimes it's handy because of the way we're starting a problem. It's more obvious if you have those variables squared up front. Okay, let's go ahead and look at another one. Let's look at 9s to the 4th plus 18s squared plus 9. Right off the bat, I see a nice little GCF here, so I'm going to pull out that 9s to the 4th plus 2s plus 1. Now it may not seem like we have, sorry, this is a squared here. I'm just copying it down. Now it may not seem like we have any perfect squareds here, but 1 is a perfect squared. It's 1 times 1. And 1 plus 1 is 2. So this does factor. Now my front positions here will be s squareds, because s squared times s squared is s to the 4th. My last positions will be 1 times 1 is 1. And I know that they both have to be a plus because of this sign right here. So my final solution would be 9 times the quantity, s squared plus 1, quantity squared. Okay? Now, GCF is important. Whenever you have a GCF, you want to pull it out first so your numbers are smaller and things are a little bit easier to work with. So the name of this assignment was Factoring Trinomial Squares and the Difference of Perfect Squares, and we have not looked at a difference of perfect squares yet. So that's what I would like to look at next. Let's look at v squared minus 9, and our rules are here to factor. So v squared is called a perfect square because v times v is v squared. 9 is called a perfect square because 3 times 3 is 9. And a minus sign is not addition, it's subtraction. It's called the difference. So you can see that what we have here is the difference of perfect squares. Now the cool thing about the difference of perfect squares is the outside and inside terms are gone. I only have my first term and I only have my last term. So when I start setting this up, the difference of perfect squares always factors the same way. They factor into a plus and a minus, and then whatever the square root is of my last term. So it factors into v plus 3, v minus 3. This is called the difference of perfect squares, and this will happen every time. Now as a quick note, there's no factorization for the sum of perfect squares. There is no factorization for the sum of perfect squares. Okay, so a squared plus b squared is prime. Prime means it does not factorable. It is not factorable. So this is supposed to say note. Let's do another note here. Prime, like a prime number like 2 or 5 or 7 or 11, it means they're not factorable. So saying something is prime is the same as saying it is not factorable. Okay, so some important points there, because this idea of difference of perfect squares really comes up a lot, and if we can see those and identify them, it's going to be a lot quicker process for us. Let's try negative 16 plus w squared. Directions are to factor. On this one, I would rewrite this right away as w squared minus 16. I just switched the order, the signs are the same. Now again, this is that perfect perfect difference of perfect squares, that special case. And the difference of perfect squares always factors into a product of conjugates. Now in our last problem, I didn't mention the word conjugate, but I will now. A conjugate means they only differ by the sign. So the conjugate of v plus 3 is v minus 3. The conjugate of v minus 3 is v plus 3. So these are called conjugates. And the difference of perfect squares always factors into a product of conjugates. So difference of perfect squares factors into the product of conjugates. Okay, so over here, to start off with, w squared is w times w. Square root of 16 is 4 times 4. So in each of these front positions we have a w and a w. Square root of 16 is 4. 4 times 4 is 16. And then the conjugate comes into play. Now why the conjugate? Up here in the problem we just did, if I multiplied this out, I'd have a minus 3v plus 3v. For my outside and my inside terms, they'd cancel. 3 times negative 3 is negative 9. Now down here, if I wanted to check my work real quick, I'd have w plus 4 and w minus 4 using my box method. I'd have w squared plus 4w minus 4w minus 16. Now notice along this diagonal goes to 0, and I'm just left with w squared minus 16, which was my original problem. So again, none of these problems should you get wrong, because you can check them all and go back and fix them if you're getting the incorrect answer. Let's go ahead and try quite a few more difference of perfect squares. And again, it's a good idea to get in the habit of checking these, so we'll be checking these along the line as well. Let's try 49 minus b squared. Let's factor. And again, difference of perfect squares. Now when I try and factor the difference of perfect squares, it might be helpful if I pulled this negative b squared out front and rewrote this. Because this coefficient is negative, I want to leave these in the same order as they're written. So we leave this as 7 times 7 and b times b. Okay, so I'm going to use that idea of the conjugates. 7 and 7, b and b, and then my signs alternate, positive and negative, because I have conjugates. Now I can't write these as quantity squared because the signs are different, so it's really not like multiplying it by itself. Okay, like I said, we should probably be very careful and check our work here. So I'm going to check 7 plus b, 7 minus b. You could also FOIL this out if you like using the FOIL method better. 7 times 7 is 49. 7 times b is 7b. b times negative 7 is negative 7b, and negative b times b is negative b squared. Now along this diagonal, this goes to 0, and I'm left with 49 minus b squared, so it checks. And remember, on your test, you can check every single one of these before you decide what your solution is. So you really shouldn't miss those. Let's go ahead and try x squared plus 1. And our rule is to factor. Now this is not the difference of perfect squares. If you notice, we have a plus sign here. This is the sum of perfect squares. Now right away we need to remember sum of perfect squares means prime does not factor. Okay, so that's our answer. This is prime does not factor. But what if we thought it factored? What if we tried to make something of this? So for instance, we're talking about the x squared plus 1, and we might think, okay, so this is wrong, but I'm going to show you why it doesn't work. We might think an x and an x goes in each of my front positions and a 1 and a 1 in the back, or same setup, and then I need a positive here. So if both my signs were plus, that would give me an x squared and a 1. And if both my signs were negative, that would also give me an x squared and a 1. But when I FOIL this out, I'd get x squared plus x plus 1. And here I'd get x squared minus x plus 1. This one would give me x squared plus 2x plus 1. This gives me x squared minus 2x plus 1. Notice, this does not equal x squared plus 1. This one does not equal x squared plus 1 either. So that's why we say it's prime, it doesn't factor. There's no way I can get those outside and inside terms to cancel to 0 unless I work in the complex number system, and we are focusing on the real number system right now. So again, it's really important that we check through those. Both of these factorizations are wrong. Don't fall into that trap. A lot of people just see two terms in a perfect square and they just go ahead and do the conjugate bit, and it just doesn't work. Let's look at 9v squared minus 16, and let's talk about factoring these. Well, I see perfect squares. I see 4 times 4, and I see 3 times 3. So let's go ahead and set it up. 3v, 3v, 4 times 4. Conjugate, plus and minus. So there's my solution. So this one was the difference of perfect squares. So again, we have that conjugate going on. Now we should check our work. So I'm going to have 3v plus 4, 3v minus 4, and again, if you'd rather use the FOIL method, that's fine. So here I have 3v times 3v is 9v squared, 3v times 4 is 12v, negative 4 times 3v is a negative 12v, and negative 4 times 4 is a negative 16. Negative 12v plus v 12v goes to 0. I'm left with 9v squared minus 16. And that matches my solution, so I know I have the right answer. So again, I think I've said this a few times, but you should not miss any of these on a test, because you should be able to check every single one of these problems before you submit them. Okay, this is a doozy. Okay, first of all, on this one I see a GCF right away. I notice that there's a b that's in common for both of these. So I'm going to go ahead and factor out that b. I'm left with 64 minus 121b squared. Now 64 is a perfect squared, it's 8 times 8. 121 is a perfect squared, it's 11 times 11. So this is going to factor into 8's in my front position and 11b in my back or my last positions. And my signs will alternate like a conjugate. So to check my work here, 8 times 8 is 64, minus 88b plus 88b goes to 0. 11 times 11 is 121b squared. Positive times a negative is a negative. So again, there's several ways to check these, but remember what we looked for here on this first one was a GCF, a greatest common factor. Okay, let's go ahead and look at a few more problems. I think we'll do 4 or 5 more just so you have plenty of practice. In these next problems, we're still factoring, just different types, and I want you to see lots of good examples so when you do your homework they're familiar to you. Let's try x squared minus 16. Actually, let's change that. Let's change it to x to the 4th minus 16. Okay, well I see difference of perfect squares here right away. So our rule is to factor, and I see difference of perfect squares. And you might say, well, wait a minute, x to the 4th. Well, what that is, that's x squared times x squared, and 16 is 4 times 4. So again, difference of perfect square. Now in my front position, I'll have x squareds, and in my back positions, I'll have 4 times 4 is 16, and then my signs will alternate. Now I can't say I'm done with this one. For this part, remember, this is the sum of perfect squares. This x squared plus 4 is the sum of perfect squares. Okay, so here, this one is prime because it's the sum of perfect squares. However, this one I can factor further. So when I say factor further, I would have x squared plus 4, and then how would x squared minus 4 factor? It would factor into x plus 2, x minus 2. I want to change the colors on these so we can see the difference. So this one was x squared minus 4, and then this one factors down into x plus 2, x minus 2. One more level, difference of perfect squares. Now x squared plus 4 does not factor further because it is prime. And remember, if something is prime, you cannot factor it further. It's not factorable. Okay, this next one we're going to have some pretty big numbers. So the first thing that we might want to think about is a greatest common factor. So I look at 6 and I look at 486 and I see that they're both even, so they're both divisible by at least 2. And I think 486 is divisible by 6. So let's go ahead and pull that 6 out. We'll be left with c to the 4th minus 6 times 8 is 48. 6 goes into 6 once. So I have the 6 out front, and again my job was to factor this. Now if you notice, c to the 4th minus 81, this is the difference of perfect squares. Okay, so I have the 6 out front. Now this is going to factor into c squared, plus 9, and minus 9. Again, it's that conjugate. And I forgot to use a different color here. I'm going to run back and use a different color. Call that c squared minus 9. Now c squared plus 9 is prime. So this piece right here is prime, so I cannot do any more with it. But this piece is still the difference of perfect squares, same as the one above, so we need to factor further. And this one factors further into c plus 3 times c minus 3. So my final answer here is 6 c squared plus 9 times c plus 3 c minus 3. So that one factors, there's a lot going on there. That one factors a lot. So when we get done, the first thing we look through is GCF, greatest common factor, and then I just keep looking at it to see, will it factor any further? Do I have a difference of perfect squares? Is there any perfect squares? Is there any way I could factor this further using the AC method? Let's look at 1 minus a to the 8th. Our rules are to factor. Now when I look at 1 minus a to the 8th, it doesn't look like difference of perfect squares because a to the 8th doesn't look like a perfect square. But I would like you to note something here. A to the 4th times a to the 4th is a to the 4 plus 4. When you multiply like bases, you add exponents, and I get a to the 8th. So a to the 8th is a perfect square. It just doesn't quite look like one. It's kind of in disguise. So, difference of perfect squares, even though it doesn't quite look like it right away. And we'd write this out in factored form. Put our parentheses up. We'd have a 1 plus a to the 4th and 1 minus a to the 4th. Again, those are our conjugates. Okay, 1 plus a to the 4th is prime. 1 minus a to the 4th is the difference of perfect squares, so I should factor further. So I have this 1 plus a to the 4th. Oh, I forgot to do my colors again on this. This is 1 minus a to the 4th. This is going to factor into 1 plus a squared, 1 minus a squared. And that's because a squared times a squared is a to the 4th. Now I note this one is prime. This second term is also prime. 1 minus a to the 4th split here. Now this one is still the difference of perfect squares. And then, of course, we need to factor further. Okay, so drag everything else along. 1 plus a to the 4th, 1 plus a squared. Now, 1 minus a squared is going to factor into 1 plus a, 1 minus a, conjugates, and this is my final solution. So again, you have to keep with some of these. They get pretty long, okay, but once you recognize things like a to the 8th is a perfect square, using your rules of exponents, they're not too bad, but you do need to keep breaking them down and kind of sticking with them to make sure that there's no further factorizations that you can do. Let's try s to the 12th minus 81. Again, our rules are to factor. Note, doesn't seem like s to the 12th is a perfect square, but it's equal to s to the 6th times s to the 6th, because when you multiply like bases you add exponents. So this is actually s to the 6th times s to the 6th, and 81 is equal to 9 times 9. Okay, and then because there's a minus sign here, we know it's a difference. So this is going to start out as s to the 6th plus 9, and then s to the 6th minus 9. Okay, this one is prime. This one is still the difference of perfect squares. I can factor further. Now the note that I want to make here, s to the 6th is equal to s cubed times s cubed. When you multiply like bases, you add exponents, and so I can see that the square root of s to the 6th is just s cubed. So here I'd have s to the 6th plus 9, and then this one factors further. S cubed plus 3, s cubed minus 3. Now I'm done with any perfect squares, and so I get down to my final solution here. This is completely in factored form. So again, you got to stick after these. You know, they're not all that easy sometimes, but just keep breaking it down using those ideas of perfect squares. Let's look at one with a fraction, w squared minus 1 over 16th. Now this is the difference of perfect squares as well, because on this one, let's note 1/4 times 1/4 equals 1 over 16. So it's a difference of perfect squares. The square root of w squared is w. The square root of 1/16 is 1/4, and of course we use the conjugate. So this checks as well. So these can only not show up in variables and everything else. They can also we can also look at these in terms of fractions. Okay, one last problem. Speaking of fractions. So let's look at 36 minus 1/9 a squared. Directions are to factor. Square root of 36 is 6 times 6. The square root of 1/9 is 1/3 times 1/3. And square root of a squared is a times a. So this is a difference. So this is a difference of perfect squares. So when we set up our difference of perfect squares, we're looking at conjugates. So let's put a 6 in each of our front positions. And again, we can check these when we're done. Whoops, got to get a pin here. Let's put a 6 in each of our front positions. Now each of my back positions will have a minus 1/3 a. Okay. Now, my signs aren't correct here though. Remember, the signs have to alternate, positive, negative, or negative, positive, because we're multiplying by conjugates. So these are working with lots of perfect squares, either the difference of perfect squares. Remember that the sum of the perfect squares is prime, meaning it's not factorable. Now, just because a trinomial has a perfect square in it is not guaranteed we're going to use it, but it's usually a good spot to start when factoring, and it might be a little bit shorter than using the AC method or the reverse FOIL method. Good luck on your homework, and please let me know if I can answer any questions.